What we're going to look at is how to use and or calculate a term called enthalpy, which we use a capital H as a variable. It turns out enthalpy is a thermodynamic kind of process or value of chemical or physical properties. And enthalpy is defined as the H equals U plus PV. So what are these? U is the internal energy in a system, and P and V are pressure and volume of that system. Now it turns out that all three values, U, P, and V, are referred to as state functions. State functions are essentially values that only rely on the actual value at that time, but not how that value was achieved. So a classic example is altitude on top of Mount Kilimanjaro. There are really, in this diagram, a couple different ways that you could get to the summit of Kilimanjaro and be at that altitude of 19,000 plus feet. You could start at the base camp and go in a single line directly up to the summit, or like most people, go through traveling through a path of switchbacks to the top. One requires a longer distance to get to the summit, but at the end, the summit is still at the same altitude no matter how you got there. That is likened to a state function. The only problem with the U and the P and the V within the enthalpy equation is the fact that we can't actually measure, it directly. However, we can measure changes in enthalpy. And so if we rewrite this equation where we put the symbol change in front of enthalpy, U, and V, and we assume that we're at a constant temperature, then we can rewrite that equation like so. And it turns out that these values, delta U, is actually can be defined as a value of Q plus W, which is the amount of heat energy plus work. And then P times delta V can be defined as a term called pressure times the change in volume, or pressure work. And that can actually be set equal to negative W. If we plug these two values back into that equation in place of those particular sections, then we get a value that looks something like this. Delta H equals Q plus W, and then P times delta V equals minus W. And if that's true, then the two W's cancel, and the delta H at constant pressure is actually equal to Q. And Q is the value that we have been measuring in calorimetry. So delta H in constant pressures of chemical reactions is equal to Q. So this is how they relate to one another. There are some rules for using delta H. These rules, I'm going to start with rules 1. The rule 1 states that the delta H value as shown in the chemical reaction is true. Okay, so for the chemical reaction that I've written here is hydrogen gas plus half of a mole of O2 gas yields H2O liquid. This delta H for this reaction has been experimentally determined before and is given to us as a value of negative 286 kilojoules. What this means is that the delta H for this reaction is true only if a 1, a 1/2, and a 1 are the coefficients in this reaction. If you change those coefficients, the delta H value also changes to the same degree. So for example, if I take the entire reaction and multiply it times 2, each coefficient, that then becomes 2 H2 plus O2 gas, 2 times 1/2 is 1, yields 2 H2O. Then the delta H must then also be times 2. So that gives us a value of 286 times 2, which ends up being 572 kilojoules. That's negative. So these delta H values are associated with the coefficients, and they can change. Sorry about that. They can change based on how much you change the coefficients. The second rule for using delta H's is that the delta H is also dependent on the physical state of the reactants and products. So in this particular case, you will see almost all chemical reactions written with their subscripts of what phase a particular substance happens to be in. Because it turns out the delta H for water in gaseous form, it has a lower value of kilojoules than the delta H of water that is in liquid form. And so those phases actually matter. So it's important to make sure that you're paying attention to that and taking those into account. The last step is, or rule, is that the sign of delta H actually means something. So when you have a negative delta H, that means that that particular chemical reaction gives off that amount of energy and then therefore is considered exothermic. And if you have a positive delta H, that chemical reaction takes in that amount of energy and is considered endothermic. So for every chemical reaction I've written before, these have all been negative, and therefore all of those chemical reactions those delta H's are associated with are exothermic. So let's go through and see if we can do some values, calculations with them. So this particular problem states it has a chemical reaction. It's a fairly long chemical reaction, and it has some pretty large coefficients to it. Let's keep in mind all of those coefficients. And essentially, you have this substance, sucrose, that reacts with potassium chlorate to produce carbon dioxide, water, and potassium chloride at a certain mole ratio. And the reaction, the question says that if you started with 7.19 grams of potassium chlorate and it reacts with excess sucrose, it produces this amount of energy in the value of 43.7 kilojoules. So that means right now, given with the mole amount of potassium chlorate that you have here, the energy given off is negative 43.7. It says now, determine the enthalpy change for the reaction, and what they mean, what this problem means, is for the reaction written up here. So essentially what we're going to do is we need to figure out how many moles of this 7.19 grams is present, and that many moles produces this amount of energy. And then we need to translate that to the reaction's value of moles of 8. So I'll show you how to do this. So we start with 7.19 grams of potassium chlorate, and we're going to convert that to moles. And potassium chlorate's molar mass is 122.55 grams. And that is equivalent to 1 mole of KClO3. Let me write KClO better. And that mole value rounded to the third significant figure is 0.0587 moles. So essentially what we know right now is that for every 0.0587 moles of KClO3, it produces 43.7 kilojoules. So, however, this chemical reaction written up here says that whenever KClO3 reacts with sucrose, it's 8 moles that reacts with 1 mole. And so for us to find delta H for the reaction, we need to translate our value down here to 8 moles. So this is what we do. If we started with 8 moles of KClO3, how many kilojoules would that be? Well, we can just use this guy up here as a conversion factor. We know for every 0.587 moles of KClO3, that makes 43.7 kilojoules. And so we can just do our math fairly quickly. And if we multiply by 43.7 and divide by our 0.0587 moles, it gives us a value rounded to the third significant digit of 5,960 kilojoules, because the moles cancel out. So the delta H, theoretically, for this reaction is 5,960 kilojoules. That would be your answer. Now, it turns out that enthalpy changes, or delta H, can be discussed in other types of chemical or physical properties. And they're no different than what we just saw in how they are written and discussed, except for they are for specific kinds of chemical reactions. So for instance, this first example would be example of enthalpy of combustion. It's called enthalpy of combustion. And all it means is it's the delta H for a specific kind of reaction, and the kind of reaction is called a combustion reaction. It's calculated the same way, it means the same thing, but it just is written because as a combustion type of reaction. And a combustion reaction, remember, has a hydrocarbon that reacts with oxygen that produces CO2 and water. And we typically write the delta H with a C as a subscript, just to say, hey, enthalpy of combustion. Another way that you could actually talk about and use enthalpy changes for other chemical processes is one that stands for the standard, and I miswrote the word standard. So this is standard enthalpy of formation. So this one, oops, go back. This one's standard enthalpy of formation. We write as delta H with a subscript F, meaning formation. And what we're forming is a compound, or formation of a compound from elements. So you'll only see a standard enthalpy of formation written where the reactants are considered elements and the product is considered a compound. Now, most delta H's that you get are going to probably be written in one of these two ways, either combustion forms or formation forms. Not always, but if you're going to look them up in a table or something like that, that's probably the way you'll find them. The really cool thing about the standard enthalpy of formation, though, is this neat thing that I want to show you about this topic called Hess's law. I keep erasing rather than highlighting, so here we go. Highlighting Hess's law. And Hess's law is really neat because it states that the enthalpy change can be written as a sum of several stepwise processes, which means, guys, I can take the enthalpy of formations and other chemical reactions, and I can add all these chemical reactions together to form and sum up together a brand new chemical reaction that maybe you couldn't find in a table somewhere. So let's do an example of that. And it says here, calculate the delta H naught, and this just means for the reaction given for the process. And I did kind of brush over and didn't really talk about what this little circle that's superscripted for this means. And we say it as naught. And naught means a standard condition. And the standard conditions for delta H of formation reactions, or delta H reactions for the most part, are the fact that we're at 1 atm. If it's a solution, like an aqueous solution or something like that, it's 1 molar. The temperature tends to be at 298 Kelvin. And so those are standard conditions. And any time that zero, or naught, as we call it, is written on an enthalpy, those conditions are typically being met. And so the question asked again, calculate the delta H naught for the reaction for the process of this one right here. So we're wanting to know what's the delta H naught for that reaction. And you can only use other reactions with their actual given delta H naught of formation values. And you have to use these two that I gave you. One of them is mercury in liquid form with chlorine gas, gives you mercury chloride, or mercury 2 chloride that's a solid, and the delta H naught of formation is negative 224 kilojoules. And then there's another reaction that says mercury liquid reacting with mercury 2 chloride that's a solid, gives you HT2Cl2 that's a solid, and its delta H naught is negative 41.2 kilojoules. See, neither one of those reactions has exactly the same reactants or products, but they have a combination of those. So this is how Hess's law works. As it turns out that you can sum up reactions along with their delta H naught of formations, and you can actually flip reactions to put products on reactant side and reactants on product side in order to build. So essentially you're going to use these to build the reaction above. And if you flip a reaction that's over here in this side, then you have to flip the sign of the delta H. So let me show you how this works. So essentially I'm wanting to build this reaction up here. So I know, first of all, I have to have a reactant as Hg2Cl2. So find a reaction below that has that value, or that substance, and it turns out here's the substance. And so what I'm going to do is I'm going to use that chemical reaction to put that substance as a reactant. So I'm going to rewrite this chemical reaction, but putting this as a reactant. So I'm going to put Hg2Cl2 solid, and then I'm going to flip it. So what used to be reactants are now becoming products, HgCl2. And then I need to associate the delta H naught with it. And the delta H naught is for 41.2 kilojoules, but see, this time it was negative, but I flipped the reaction, so I'm going to make sure that says positive. So now I have the reactant on the reactant side. But now I need to make sure that I have both products. I have mercury. It turns out I do have mercury did move over here. But see, I don't have chlorine yet. So I need to get chlorine over on the product side. So I'm going to use that reaction now, and I'm going to flip that reaction to put chlorine as a product. And so I'm just rewrite the whole thing. So HgCl2 yields HgL plus Cl2 gas. And I'm going to put my delta H naught of formation is 224 kilojoules, but make sure that that's now positive. We're switching the sign. And essentially now what I have is my chlorine in the product. So I've got reactant, product, product. And it turns out that second reaction even had another version of that product of mercury, and that's okay. So what you'll do now that you have built your reaction with these other chemical reactions, you add everything together. Add the reactions, substances, and the delta H's. So I'm going to write everything again. Hg2Cl2, which is solid. And I'm writing everything that's on the reactant side together. So this will be plus HgCl2, solid. And then I'll put yield sign. And then I write, these are the same thing, so I just collectively add them together, and I'll just say I have two of them. Plus HgCl2 plus the other chlorine gas. And then I'm going to add my delta H's together. Delta H naught is, and this will be what, 265.2 kilojoules. So we need to make sure that this reaction right here looks exactly like this one. And so what we'll do is we will take anything out that is the same on the left and the right. It turns out that this guy right here and this guy right here, they're on the left and the right. So it means they're not actually a part of the reaction. We can take them out. There's nothing else like that, and actually the coefficients match exactly with the reactant above, or the reaction above. So we can just write our final answer is Hg2Cl2S yields 2HgL plus Cl2 gas, and our delta H naught. And we should put this in proper sig figs, so the one's place is 265 kilojoules. So that is the enthalpy of change for this reaction. And it's just beautiful that the Hess's law allows us to do that. Okay, that is enthalpy. We will do some more problems in class, so I will see you next week.